we are going to plot them and try to figure out whether it is a linear regression or a quadratic regression. Okay, so let's remember how we do that. Let's start with problem number 2. Let's do problem number 2. Now, do you understand, even though the table was written sideways, that may look a little confusing to you? Those are really just a set of ordered pairs. The first point is 0, 2, and then 1, 3, and so on. So remember how to do that. We go to Stat, Edit. Now, I have a ton of stuff already in there from other problems. I can either type over them or I can clear them out using clear list, or somebody told us that we could just highlight L2 and hit clear and it would clear it. And highlight L1, hit clear, and it would clear it. So however you do it, we're putting in the points from problem 2. So 0. Once I have all the numbers in, remember, we want to graph these, but in order to graph them, make sure your window, go to your window, and make sure that your x-min and max will accommodate 0 to 5. So I may put in -2 to 8. Nothing sacred about those numbers. I just need to make sure I get something on either side of 0 and 5. And my y's are 2 to 27, so I might go 0 to 30 on my y's. Now, if I hit graph, I get some funky equation because I have something in there for y equals, so I'm going to have to clear that out. How do I get it to plot those points? What do I have to tell my calculator to do if I want to plot those points? I have to go to Stat Plot and turn it on. And then it will plot the points. If you forgot how to do this, look over on your neighbor, have your neighbor help you. It'll plot the points, and mine look kind of like this. If I connect those dots, what kind of a shape am I getting there? Because that's the next thing I have to decide is, do I have a linear regression or a quadratic regression? What do you think? Quadratic. Now how do I, okay, so now I want to match it to a graph, so that shouldn't be too bad. I ought to be able to match it to a graph there. But then I also have to match it to an equation. So how do we get our equation? Remember? Go back to Stat and over to Calc, and then all the way down to Quadratic Regression, because that's what you thought it was. And something happens there that we need to talk about. Since you did Quadratic Regression, you're going to get a parabola, get a quadratic equation. And it says A is 1. Now, what does your B say? Does your B say 1.3 e to the -12? Okay, that means 1.3 times 10 to the -12. That's scientific notation. Tell me about that number right there. It's really small. It is so small that it is essentially what? 0. So we're going to interpret that as 0 every time we see it. Now, a few of you have already encountered that in your graphing. The calculator is very sensitive. It has round off error because it does everything logarithmic, but it also can carry a bunch of decimal places. So sometimes, because of the round off error with the logarithms, you end end up with not quite 0 when it really should be 0. This should be 0. You just have to know when you see something like that, think of it as 0. It's going to happen a lot on your, or not a lot, but it'll happen quite often on your calculator. So here's my equation that matches that set of points. So then I go back to the book and okay, so what matches problem number 2? It looks like picture looks like picture F. The letters go with the one above. So it looks like picture F, and its equation is R. Equation R. We're just matching. All right, so let's try one more. Let's try number 5. All right, start all over again. We're going to do problem number 5. Okay, so what do we have to do first? Got to put in, well, yeah, you got to put in your new data, which somehow you got to get rid of your old data. Either type over it or clear it out. We're on problem number 5 now, so we're putting in all of our x's. Oops. All my x's in. And then I'm putting in my y's. Okay, then just use the first 2 columns, whatever they are. Okay? Now, once I get all my points in, then what do I do? Yes, very good. Change your window. Because the window we had before isn't the right size to accommodate all these points. Now, my x is okay. My x window is still okay. I went from -2 to 8, and will that cover my points in my x column? Yeah. But my y's this time have to go from 39 to 4. So I'm going to go from 0 to maybe 40. Now my plot is still turned on from the last time. So when I press graph, up they come. I got it. Remember, if you press graph and you don't see your points, your dots, then either your window's not set right or you forgot to turn the plot on. If you want it to graph, plot points, you have to tell it plot points. All right? Then what do? Once you see your points, you have to decide what? You got to decide if it's quadratic or linear. I think this looks quadratic again. It looks like a parabola opening down. So I'm going to go back into Stat Calc and pick quadratic again.
Is it just quadratic?
Mm-hmm. That's quadratic regression. And what did you come up with for that one? We got that same funky thing going on there with that E thing. So my equation is what? What'd you get? Negative x squared
Plus 40.
plus 40. The B term again is 0 because you got that weird E thing. So matching, that was the purpose of the exercise, matching. The equation is L, and the picture is E. So in that set of problems, that set of exercises, that's what you're going to be doing. Now, remember, every time you hit graph now, those points are going to come up. Even if you don't want them to, they're going to come up. Unless you go back and turn your stat plot off. As long as that stat plot's on, you're going to get those points. So if you don't want to see those points anymore, you go back back into stat plot and turn it off. Okay, let's look at a couple more problems. Same group, but now on page 82, number 20. Problem number 20. All right, so you're going to go in. Oh, by the way, speaking of buying cakes, today is Dr. Greer's birthday, so wish him happy birthday, send him an email, something. A bakery sells a 9 by 13 cake, okay, for the same price as an 8-inch diameter round cake. If the round cake is twice the height of the rectangular cake, which option gives the most cake for the money? Okay, so you're going to go in and buy Dr. Greer a birthday cake, and you want to get the most cake you can. So tell me what your thought process is. Find the area. Find the volume. Which do you think? Do we want area or volume if we want to get the most cake that we can? That'd be volume, wouldn't it? I want the biggest volume I can. So this is like just a rectangle, 13 by 9 cake. I need to know the volume of it. It's a rectangular solid. It's a rectangle. How do you find the volume of a rectangle? A rectangular solid? Length times width times height. And yes, you're supposed to know that. That's one of the things by this point in your life you should know, that the volume of a rectangular solid, a box, the volume of a box is length times width times height. So we have a 9 times 13. Now, do I know what the height of this is? No. All I know is that this one is 2 times it. So let's just say this is 1 inch, and then this height will be 2 inches. If you want to make this 2 and this 4, that's fine. We're not finding the actual volume, we're comparing the 2 volumes. That's what we're doing. So it doesn't matter what you make the height. So if we make the height 1, this is, what, 117 cubic inches? Check my arithmetic, I think that's right. Now, you got your layer cake here, your round layer cake. It's twice as high. What's its volume? Well, what shape is it? Think of that round layer cake. What shape would that be? It's certainly not a rectangular solid. It's not a box. What do we call that shape? A cylinder. This is going to be a cylinder shape. What is the volume for a cylinder? The area of the base times the height. What shape is the base? What's the area of a circle? Pi r squared h. There is your formula for the volume of a cylinder. Pi r squared, the area of the base, times h, the height. So be careful. What's our radius? 4, so that's 16 times 2. So that would be 32 pi. All right, type that in on your calculator, 32 pi. And I just need to know, is it more than 117 or less than 117? I bet it's less.
It's less. It's 100.53.
100.53 cubic inches. This cake is probably prettier, but it is smaller. And so if you're all about getting the most for your money, you're going to buy this one. Does that make sense to you? All right, let's look at another one just like that, number 21. We can buy 12 by 12 stepping stones, like you put out in your yard or garden or walkway or whatever, for the same price as 13-inch round ones. If all the stepping stones are the same thickness, which option gives the most rock for the money? think about this for a minute. It's a very similar problem, isn't it? But it's different in a certain way. Can you tell me what's different about this problem?
They have the same thickness.
Well, they have the same thickness, right? And it's a square, not a, well, squares are rectangles, but yeah, the dimensions are the same. But think about what you're doing with this. You're buying these things, and what are you going to do with them? You're going to go out and put them on your somewhere, right? Are you interested in the volume of these things? What are you interested in? The area, how much it covers, the area. So we're going to do a comparison, but this time we're comparing the areas, because the purpose of this is to cover a big space. So the area, that's easy. That's 144 square inches. What's the area of this? Pi r squared, so that would be pi times 6.5 squared. What's that? Decimally speaking, so I can compare it to 144.
132.73.
Okay. So if you are interested in covering the maximum area for the same price, you will use the squares because they have a larger area. Okay, now we're going to look at problem 40. This first section, 1.1, is just a mishmash of a bunch of different kinds of problems. So we are going to solve this equation graphically by converting to an equivalent equation with 0 on the right side. So what they mean is exactly what we've been doing. Get the equation set equal to 0, graph it, and what will we be looking for? If our job is to solve that equation, what will we be looking for here when we graph this?
X-intercept.
The x-intercept. When you set your equation equal to 0, you want to find where the equation equals 0. What x's give you a 0 answer? So you are looking for those points. So we're going to graph this on our calculator. Now, I'm going to turn my stat plot off right now because I know those points are going to annoy me. So I'm turning my plot off. And now I'm going to go to y equals, because I'm going to type in this equation right here. Now, to get absolute value on your calculator, all right, everybody go to y equals, so you're ready to type in your equation. If you go to math, which is right here, math, and you click over to number, NUM, the very first option there is absolute value, right? So you just hit enter. Now, some of them bring up the bars, some of them bring up parentheses. It doesn't matter. Once you hit absolute value, type in 3x minus 2. Now, on my calculator, I have to close the parentheses. Some of the new ones, you don't have to do that, but I close the parentheses. And then minus 2 times the square root of x plus 8. And I close those parentheses again too, and hit graph. Now, what I see is this, actually. That's what I see. I'm not real comfortable with that at all. I don't think I'm seeing enough. So I'm going to go back and change my window. And I really need my window to go down farther. So I'm going to change y-min to maybe -10. And now I see something that looks like this. Now, remember, there is no exact window, but you already told me, what do I need to see? I need to see the x-intercepts. So if you're not seeing x-intercepts, make your window bigger so that you can see them. Oops. All right, so now we know how to find those, right? Everybody knows how to do that. Second calc. So I got one of my solutions to be 2.864. And I got the other one. Negative 1.149. How do those look to you?
Yeah, negative 1.08. That's what I got.
Uh-oh.
I got 1.06 and maybe 1.06.
Make sure. Do we match on that one?
Yeah, we matched on that one.
Let me try that again, because we shouldn't be off that much. We shouldn't be off that much. So, this is all right, left down. Yeah, I don't know what I did the first time. Negative 1.086.
Yeah. As long as it's
I don't know what I did. Okay, all right, let's see. Let's try another one. There's another one we can do there. How about, what was that? That was 40. How about 45? 45, same thing, just a wacky and wild equation. So we'll get it set equal to 0. If you're going to solve using the intercepts, which I think is the easiest way, you have to do what the directions say, and that is get your equation set equal to 0. It doesn't matter whether you move everything to the right or everything to the left, but you have to move everything to one side so it's equal to 0. So now I'll take out the other equation and put this one in. And you're going to put it in exactly the way we wrote it. I have no idea what this is going to look like. This is going to be some kind of funky equation for sure.
Oh, did you get oh. Oh. Wait. Wait, I did not get it.
Very strange looking thing. I'm gonna play with my window a little bit because I'm not real happy with what I'm seeing here. So play with it for a minute. Okay, now here's what I need you to understand about your calculator. And the newer ones are going to do a better job than the older ones are. But we've got something that looks like this, and then we got something that looks like this, and then we got something that looks like that. Okay, now, if you watched your calculator graph,
it came down, and then it drew a line up like this, and then it did this, and then it drew a line down like this, and then it did this. Those aren't really lines. Those are asymptotes. The problem is, I can pick up my pen, but the calculator can't get from up here, or from down here to up here, so it just goes zoop and makes a line, but that's really an asymptote. So the curve is coming down here, and then there's another piece of it up here, and then there's another piece of it down there. Those of you who have watched the 1.2 video know that this is a discontinuous curve because it is in pieces, 3 distinct pieces. And why is it in pieces? Because what does a -1 exponent mean? It means it's a fraction. It means 1 over. And those of you who watched the 1.2 video know, what does that mean? X can't be -1, so there is a vertical asymptote at -1. What does this mean? 1 over x. That means x can't be 0, so there's a vertical asymptote at 0. So the curve is literally broken in these 2 places. So the calculator graphs over here and here and here. Remember, if you watch the video, the conversation about increasing, decreasing, I said graphs are read from left to right. Well, they're drawn from left to right on the calculator, and so he can't pick up his pencil. So he looks like they're connected, but they're not. They're 3 distinct sections. Regardless of whether you watch the video or not, which you need to watch it, how many x-intercepts do we have? 1. So the only solution to that equation is that point right there. So even if your picture looks wild and wacky, you can find the intercept. Just keep pressing the arrows. It'll come down to the right curve. Remember, the curve's in pieces, and you gotta keep pressing your arrows until you get the right piece. I got -1.466.
Oh.
Did I get that one right, or did I miss
Yeah.
that
I got
one?
positive 1.46. Probably go back to your right.
All right, and now I want to talk about one more thing. Hasn't been an issue for us so far. It really isn't a huge big issue, but we do need to be aware of it. Look at number 51, problem number 51. We need to be aware of what's called hidden behavior. So I'm on number 51, and I'm going to graph this on my calculator. Okay, come to graph that just like I've done. Those of you who watched the video, will this guy have any asymptotes? No way, Jose. Where do these vertical asymptotes come from? What do you have to have a vertical asymptote? You gotta have a fraction, you gotta have a denominator. We do not have that here. This is a nice little polynomial function. Got some wacky numbers in it, but it should be easy to graph. Now, I left my window the same as the last problem, so I used a standard window, that we call that a standard window, -10 to 10 on both, and
I see it going up like this, and then there's a piece that does something over here. Now, do I care about what's going on up here? I mean, I could be curious about it, but for purposes of solving this equation, I have no interest in what's going on up here. This is what's interesting, right? So this one is no problem. I'm going to find that one first. Second calc, absolutely no problem finding that 0. Now again, if you don't see the cursor on the screen, you got to just keep viewing your arrow buttons till it comes on. It will come on. Oh, I got exactly -3 there, did you?
Yes.
Now, so I got that one. I'm done with that one. So one of my answers is -3. I am not concerned anymore with this part of the picture. This is a little bit awkward on my calculator with my window. It looks like it touches, but I'm not sure if it does or not. So I'm going to go ahead and I'm going to blow this up. I'm going to blow up just this part of the graph. So how do I do that? Well, I'm going to go to my window, and I'm going to change my x-min to 0, and my x-max to maybe 3, and see what that does for me. Now, can I clear, if you do that, I set my x-min and max at 0 and 3. Can I clearly see that it crosses now? Or that it touches now? Okay. Now I'm going to change my y's. I'm going to leave it 0 to 3 for that. I'm going to change my y's. Okay, get this, to -0.1 and +0.1. So I am really shrinking that. Now I got back to this funky looking shape again, but what do you notice about it? It goes below the x-axis. This actually goes below the x-axis. I wouldn't have known that until I changed the size of my window. Do this for me. Make your, oh shoot, I don't know. Make your x's 1 to 2. 1 and 2, and let's see if that, yeah, there we go. So make your x's from 1 to 2 and your y's from -0.1 to +0.1. Now do you see that shape clearly? So in the beginning, I thought maybe there was one intercept there. Well, it turns out actually there are 2. And I only knew that because I examined it a little bit more closely. And how did I do that? By zooming in on the picture, by making my window much smaller. It started out -10 to 10. Well, I got it down to 1 to 2. So I'm only looking at a little piece of the graph. And now I can see that there are 2 intercepts in there. And I would do second calc to find each of those. It's going to take a while to get that cursor on, but you can do it. 1.1. One of them is 1.1. If I did that right. And the other one is going to be close to that. 1.15.
Yep.
Hidden behavior. Sometimes when you graph, you have behavior that you can't see. So if something looks a little unusual in the picture, like I wasn't sure if that touched or not, investigate a little bit farther and just check it out. Okay? All right, that's enough. I think we've got you through 1.1. So now we're going to get out our BFF sheets that I handed you out today. Some of you maybe wondered why I have these Coke cans over here, but I thought this was so cool. BFF, our basic family of functions. There are 12 functions that are called the basic family of functions. You need this too. 12 functions that are called the basic family of functions, and you're responsible for knowing them. So today we're going to get started on that. You'll notice, those of you that have watched the video, the list of information there, we've got some vocabulary that we are familiar with if we've done the 1.2 video. I would strongly suggest, if you haven't done that, that you get busy on that. Okay, the functions are named. You are responsible for the name, the equation, and the shape of the graph. If you know the shape of the graph, then answering all those questions will be easy. I do not want you memorizing, oh my gosh, no, too much. All that stuff for each of these, no. If you know the name, the equation, and the graph, you will be able to fill in all those things as you go, okay? If someone said to me, Lisa, what's the range of the exponential function? I would sketch it. In my mind, I would think, okay, what's the exponential function look like? And then I would tell you that the range is everything greater than 0. But I don't have that memorized. I have the picture memorized, okay? So the first one there, the name is the identity function. The equation for the identity function is y equals x. This is discussed a little bit in the video. That is the line where x and y are equal, so it is this line right here. That's supposed to be a straight line. That's the picture. So the identity function has an equation of y equals x and has this picture. If you understand that, then when you have something like y equals x plus 3, okay, you know what that looks like, right? That looks like this. Now we're going to add 3 to it. What do you think that's going to do to the picture? It's going to take this picture and do what with it? Up 3. So you're going to have exactly the same picture, but moved up 3 units. Now let's talk about the characteristics of the identity function. Domain. Domain, and again, all this vocabulary is in the video. I'm not going to go back through it. Domain is associated with x, the input values, the x values. Tell me about the x's here. All real numbers. The domain is all real numbers. Range is associated with output. Y. What is the range of this picture? All real numbers. We love our identity. It is so uncomplicated. Continuity. When I draw this thing, do I have to lift my pencil? There's no breaks in this picture. So it is continuous. It is continuous. Yeah, you can say yes. Our classifications are continuous or discontinuous. This one is continuous. It has continuity. Increasing or decreasing. Some functions are both. Not this one. Left to right, this one is increasing. Does it have any symmetry?
Yes.
What symmetry does it have, Patty?
I believe it doesn't have a symmetry across any of the shown axes, but, well, perpendicular to it.
Okay, actually, we don't, the symmetries we discuss are the ones that are in the video: y-axis, x-axis, origin, and the line y equals x. So since it is the line y equals x, we won't talk about that one because that's the line we're doing. But what about the origin? Is this thing symmetric about the origin? If I flipped it across this point, would it be balanced? Would it land on itself? Yes, it has symmetry about the origin. Patty is exactly right. It does not have symmetry to the shown axes. So the y-axis and the x-axis, it does not have symmetry to. Would it have symmetry to this line? Yeah, it would have symmetry to that line, but that's not one of our basic symmetries. But there are, as Patty said, there are many lines out there not drawn that it would have symmetry to. But we're interested in these four. So this one has symmetry about the origin. Bonus point to somebody who watched the video and can tell me, what does it mean to be symmetric about the origin? What's the vocabulary word? Odd. This is an odd function. They're called odd if they have symmetry about the origin. Okay, boundedness. Does this thing have a ceiling?
No.
Does it have a floor? It's completely unbounded. It's going to go on forever and ever in both directions. Extrema. That means high points and low points. Some of our pictures, for example, here, this would be a local minimum. It's the lowest point on that piece of the graph. This would be a local maximum. It's the highest point on that piece of the graph. Does this one have those things? No, there are no hills and valleys, so there are no extrema of any kind, local or absolute. It just goes on forever and ever and ever. Any asymptotes at all? Any vertical asymptotes? Any horizontal asymptotes? None. This picture has no asymptotes. It just goes. There's nothing stopping it like we have here. It just goes. So there's no asymptotes. And then end behavior. Now, what we mean by end behavior is what happens to the picture what happens, our function is just y equals x. All right? This is how we classify end behavior. It's the limit as x approaches infinity and the limit as x approaches negative infinity of the problem, which for us is just x. Now in the next problem, there'll be something different here because we'll be looking at a different function. What happens as x approaches infinity? What happens to your y values? They get bigger. They go to infinity. What happens as x gets smaller and smaller and smaller? What happens to your y values? They also get smaller and smaller and smaller. Now, get that written down, then we'll do the next one, and I'll show you how that works. All right, the next one is the squaring function, and its equation is y equals x squared. You know what its shape is. What is its shape? A parabola. That is the shape of the squaring function. You memorize that shape so that when you see something like x squared minus 4, you will not be confused. because you know what that shape is, and what does the minus 4 do to it? Takes it down 4. So you're going to have the same exact shape, just down 4. Now, let's skip down to do end behavior for this one. So end behavior, the limit as x approaches infinity of x squared, that's our function, and the limit as x approaches negative infinity of our function. Okay, now we do end behavior. I skipped all that rest out. We'll talk about it in a minute. I've skipped down to end behavior. So, this says, as x gets bigger and bigger and bigger, what happens to the function itself? It gets bigger, positive infinity. But what about in this direction? As x gets smaller and smaller and smaller, or bigger and bigger negative, if you want to think about it like that, as x goes this way, what happens to the function?
It gets bigger.
It's still positive infinity, right? So both ends are pointed up. That means they're both going to positive infinity. If it's pointed up, it's going to positive infinity. If it's pointed down, it's going to negative infinity. So that's the end behavior for the squaring function. All right, now let's fill in the rest of it. What's the domain of the squaring function? What x's are you like all real numbers? Now watch it. What's the range? What are the y values?
Anything from 0 upward.
Y is greater than or equal to 0, or in our interval notation, the range would be 0 to infinity. By the way, for all real numbers, I'm okay with you using the symbol. If you want to express it as an interval, it would be negative infinity to infinity, right?
Is it always a bracket around the, like, 0?
Well, 0 is included. So it won't for all the functions it won't be, but it is for this one because 0 is included. 0 is a point on the curve. Okay, continuous. Would you classify that as a continuous curve? Can you draw it without picking up your pencil? Yes, that means it's continuous. Is it increasing or decreasing? And remember, we read it left to right. So trace it with your pencil left to right. Is your pencil going up or down? Down and then up. So for this one, we would say it is decreasing from negative infinity to 0. Isn't that where it's decreasing?
Yes.
We talk about x values now. Which x's give me decreasing y's from negative infinity to 0? And then it is increasing from 0 to positive infinity. Now notice I did not include the 0 on my increasing decreasing, because at this point I'm really not going up or down, am I? I'm steady there, just stopped kind of at that point. So all of these I'm moving down, and all of these I'm moving up. Does this picture have any symmetries? And again, remember, these are the ones I'm concerned with. Does it have symmetry to any of these special things?
Yes.
It has symmetry about the y-axis. And if you have symmetry about the y-axis, you are called an even function. This is an example of an even function. Functions can be even or odd or neither. Most functions in the world are neither. We just happen to have our first one is odd and our second one is even. Boundedness. Does this thing have a ceiling? No, but it does have a 4. So we say this is bounded below at 0, y equals 0. We're bounded below. The floor is at y equals 0. Bounds are up and down. Upper, lower. We don't have an upper one, but we do have a lower one at 0. Okay, what did I tell you Extrema were? Tops of hills and bottoms of valleys. There are no hills in this picture, but we do have a valley, right? So we have what's called a minimum. Does that word make sense to you? This would be a minimum at 0, 0. It would be both a local minimum and an absolute minimum. If you look at a picture like this, this would be a local minimum, and this would be a local minimum. But of the two, this one would also be the absolute minimum. Any valley is going to have a minimum. The very lowest one of those is going to be the absolute. Does this have any asymptotes at all? Nope. And we've already done the end behavior. Okay, so we're going to do one more. And this one, I'm going to give you the information, and then I want you to see if you can fill in all the stuff. So now we have the cubing function. The cubing function has the equation y equals x cubed. And it has a shape that looks like this. Those of you that remember graphing your trig last year, it's kind of like a tangent shape, a tangent curve. That is your cubic function, your cubing function. All right, so I want you to fill in domain, range, continuity, all that stuff. Give it your best shot. See if you can do that for these functions. And I will do it too, and we'll compare answers. So using just the picture, see if you can fill in all the stuff. Simple one, isn't it?
Not a big one.
Time to go?
Yeah.
Not a big one.
Oh, yeah, it is time to go. I am so sorry. I am so sorry. If any of you need a pass, I will write one. For some reason, I had 9:15 in my head. We're going to flex now, yeah, anyhow. I'm sorry, though. I'm sorry. I had 9:15 in my head. Compare your answers with mine. Make sure they look the same.